This is section 3.1 on exponential functions. These are the next type of functions we are going to be looking at. So the definition of an exponential function is a function f with a base of a is denoted by, or we can say written by, f of x equals a to the x. So a is our base, x is our exponent. Our base, or a, has to be greater than 0, and it cannot equal 1. So we don't want a to be a negative number. We don't want it to equal 1 because 1 to any power is just 1. And x has to be a real number, so x cannot be imaginary in order for this to be an exponential function. So to evaluate exponents in exponential functions, there's a button on the calculator. And so this button is right below clear. So when you type in, you would type in your base first and then press this exponent button. And then whatever power you're evaluating, you would plug that number in and then press enter to see what it equals. So if we do a couple of examples, let's say our function is f of x equals 2 to the x. So for all of these functions, our exponent is going to be what we plug into. And let's say that x equals 3.1. What we would do to plug this into the calculator, we would first press 2 because that is our base in our exponential function, and we're evaluating at 3.1. So 3.1 is our exponent. So next we have to press the up arrow key, which is right below clear, and then you would press 3.1, and then you would press the enter button to get your final answer. So when you plug that into your calculator, you get 8.574. It's good to round to about 3 decimal places. The next example, so what if now our function was f of x equals 2 to the negative x and x equals pi? So here we're going to plug in the base, which is 2. And once again, we have to press the up arrow because we have an exponent. And now we're going to press the negative key. So the negative key is right down here next to the decimal. And then we insert our x value, which is pi. And so for pi, you need to press second up arrow, and that gives you the value of pi, which is rounded to about 3.14. And when you do that, you should get 0.113. So here I have 2 more examples. We have f of x equals 0.6 to the x, where x equals 3 over 2. So for this one, we plug in the base first, 0.6. We do the little caret key, and then you want to put in parentheses the 3 divided by 2. If you don't include the exponent in parentheses on some of the calculators, it will only do 0.6 to the third and then divide your whole answer by 2. So parentheses is key to make sure that 3 over 2 is your entire exponent. When you plug that in, you get 4.465. For this next example, f of x equals 4 to the x. So our base is 4. We plug in the up arrow, and then we put -2. Keep in mind the negative is not the minus sign. It is this button right down here next to the decimal. And for this answer, we get 0.063. We're going to look a little bit about graphs of functions. So here, we know that this is our exponential function, f of x equals a to the x. If it is an increasing function, that means that our exponent is positive, and this is what an increasing function looks like. So from left to right, it's going up. A decreasing function, from left to right, it's going down. And this should have arrows on the end here. I'm going to add those in, because exponential functions do go on forever. So a to the negative x, from left to right, we're going down. A to the positive x, from left to right, we're going up. So a couple more characteristics. X is always the exponent. So when you're plugging in inputs, it's always going to be in the exponent of the function, and you'll have some base. So this will not say a when you have a function, it'll be a number. So f of x, or y, rapidly increases as x increases. So as x increases means going from left to right, our function, you can see, starts to take kind of a steep upward turn. So that is a characteristic of a graph. A lot of real life phenomena with patterns of rapid growth or decline can be modeled by the function. So populations sometimes follow this type of function. And without any rigid transformation, so that means without moving left, right, up, or down, the graph will always pass through 0, 1 and have a horizontal asymptote at y equals 0. So this is really important when we understand the different transformations of graphs. It always passes through 0, 1 and has this horizontal asymptote of y equals 0 if there is not a left shift, right shift, up or down shift. So that means reflections and or not reflections, but stretches and shrinks, it will still have this 0, 1, and y equals 0 for those two characteristics. So here you can see the difference between positive x and negative x, and also the difference between different types of bases. So the bigger the base, the slower the increase. So here we go from 1/4 to 1/2, 1, 2, 3, 4, and 8. If we increase the base by just 2, so up to 4, you can see instead of 8 at the end, we're get all the way up to 64. So that's a dramatic increase. This exponential functions, when we talk about how they rapidly increase. So if I were to put 5 in here, it's going to be even closer to the y-axis, goes up even faster. Alternately, when it's negative, so it decreases. So this is going to be a reflection. And the base of 4 to x, once again, is closer to the y-axis because it's decreasing more rapidly. So the last thing we're going to look at is transformations of these functions. So let's use f of x equals 2 to the x as our function. This is normally the function you see. I'm just going to add on these arrows because it goes on forever. And we're not going to use the base of 1 because 1 to any power is just 1, which is not an exponential function. So the first one we're going to look at is f of x equals 2 to the x minus 1. So this would be a horizontal shift because minus 1 is being added to the exponent or subtracted from the exponent and not from the base. So when you have a horizontal shift or something being added or subtracted in the exponent, this changes the x value of 0, 1, and the asymptote is not affected. So keep in mind here, our asymptote is always y equals 0 when we don't have a shift. And then we have a point on 0, 1. But if we have a horizontal shift, so something subtracted from our exponent, this means we're moving to the right 1. So that means this point needs to move to the right 1, which would make this 1, 1, not 0, 1. The next graph. So this is our vertical shift. When anything is added or subtracted to the base, that means we are moving up or down. Since this is a minus, that means we're moving down. So it changes the value of 0, 1, and it also changes the value of the exponent. So, or of the asymptote. So instead of our asymptote being at y equals 0, you can now see this red line showing that our asymptote is now down 1, minus 1. So it changes the y value, and I'm also going to write down here that it changes the asymptote. The next graph we're going to look at is a reflection. So in this reflection, we reflect 0, 1. So instead of it being 0, 1, it is now 0, negative 1, and our asymptote is not affected. Here, when we have a reflection over the y-axis, neither 0, 1 or the asymptote are affected. So when we have a negative in the base, our asymptote is not affected, but we do have to reflect this point, 0, 1. So you see it goes down to 0, negative 1. But when we have a negative in the exponent, that intercept on the y-axis is not affected, as well as the asymptote is not affected.